Good morning, everyone. This is the John Chappell Natural Philosophy Society Science Chat, and I am your host, Franklin Hu. And today is March 31st, 2018. So we invite you, this is, of course, sponsored by the John Chappell Natural Philosophy Society. Please visit our website, naturalphilosophy.org. And I have begun to start posting future notices for conferences. There's video conferences there, so if you ever have wondering what is going on, you don't have to wait for my email message. You can go straight to the naturalphilosophy.org site, and it should be listed on the top what the latest meeting will be. So we may not have these absolutely every Saturday. I was taking a few weeks off due to other commitments, but I will try and keep that updated. So if you come and you find out that there's nobody here, it may be because the meeting's not going on. So we invite you to go to our website, check out our forums, and join us on Facebook. And one thing I would like to bring up especially is that our conference is coming up, and actually pretty soon. This is the Critical Thinkers Conference, University of Connecticut in Stores, USA. And this is June 27th to the 30th, which is only about 2 months away. March, tomorrow's going to be April, May, June. So about 3 months for this to happen. So I myself was doing some research on this. So this is going to be held at the Nathan Hale Inn, which is actually nowhere near the University of Connecticut. And but that's where the meeting shall be. And we've got a couple people signed up. So I decided to check out what's the accommodations are and how much it costs. So I did discover that the Nathan Hale Inn is fully booked at this time, so you can't actually stay there. So I was looking to see what other available accommodations there are. So if you're cheap like me, there's a place called the Roadway Inn in Wilmington. So that's $61 a night. So that'd be about, say maybe $200 for accommodations for 3 days. If you rent a car, you can get that for about $26 a day. So that's really cheap. I'm not quite sure what the deal is with why renting a car is cheap. And you will need a car because the airport is about an hour away from this area where the Nathan Hale Inn is. And there aren't very many hotels. Like this hotel is probably about a 20-minute drive away from the Nathan Hale Inn, and there aren't that many. So if you're thinking of coming, you need to start thinking about it now because rooms are actually not that plentiful either. So, and it is, like I said, it's only 3 months away. So I would encourage people to come if they can. So I was wondering, is anyone here today's conference planning on or thinking about going to the conference? So that's, like I said, June 27th to 30th. Or does anybody have any questions about going to the conference? I have been to the conference twice, once in Washington, D.C., and another time in Vancouver, B.C. So anybody going? How about you, pal? Going to the conference? Or Michael, or Mitch, or Gene?
I like to go, but I'm not sure if my work's going to be able to let me. I'll have to wait and see.
Yeah, so it is. You don't have to go to the entire conference. Let's see. Now June. Let's see. The 27th is. See here. So well, it is kind of midweek, isn't it? There. 27th to 30th runs from Wednesday to Saturday. Now that is the deal there. Yeah, it's kind of midweek there. Well, that's why you need to think about it. It's need to get some vacation time in order to do that. Are you anywhere near Connecticut?
I'm in the Midwest. I was kind of hoping something would be a little bit closer to the Midwest. But I don't like to travel either. But I would really like to go. I'm still kind of giving it some thought, and I'm kind of hoping I can.
Yeah, it's pretty cool if you can go. I'm just kind of waiting for a critical mass to show up. Like I said, not too many people are signed up at this moment, and I'd like to see some more.
This may be a bit of a silly question for a US-based organization, but I'm just wondering, or maybe it's a question for David the Hillster or the like, but I'm just wondering, like all these conferences in the last few years have been in North America. I think one was in Canada. I'm just wondering if there are any plans in the future to hold one maybe in Europe or something like that. It's just a bit difficult. I just have to cross the Atlantic to get to one of these conferences for a few days. Do you know if there are any such plans, Franklin?
I don't think so, but I think that would be a project for you guys on the European continent. I'm sure if you wanted to float that idea and could get a couple people together. See, the problem is, and then the rest of us here in the North America would have the same problem, that have to get that expensive airplane ticket to get over here.
Yeah, and I concede there'd be more of you with that problem.
But if you can get like a group of like 10 people over to want to have a conference over in Europe, and you guys can have a conference in Europe and maybe attract a few of us Americans over, that might be something. But that would probably be something that you would kind of have to take on your own. That would be my suggestion.
Yes, I quite see that. I'll think about that. Thank you.
Yeah, because like the last time we had the meeting in Vancouver, that one of our members, basically lives there and helped organize a lot of that. So that's also a factor.
There are not too many active participants in this part of our endeavors from Europe, I think.
You got to get some more. Right?
Yeah, indeed.
Yeah, I would probably prefer a more central location myself. Maybe, some or someplace that like we've had conferences in Washington D.C. and you can always go and visit. That's a very popular destination to go to in its own right, and you can see stuff. I'm not quite so sure there's a lot to see in Storrs, Connecticut per se.
Are we going to talk about the AIRI experiment?
The AIRI experiment, we can talk about that. But I think we're going to get to the Wakefield experiment here.
Well, let's go.
Okay, let's go. So, like I said, David Eisler on email asked us a question about wanting a background on the Wakefield experiment. So, is David here? I don't see him. No, unless he's the guy on the phone.
I've written a piece on that that's published at the CNPS website.
Okay, well, certainly we'll get your opinion. Now, I'm going to share out the document that has the Wakefield experiment on it. So, well, David, if you're watching this on the recording, this is for you. So.
Thank you.
Was that David who just said thank you?
Yes, it is.
Oh, there you are. Okay, great. You must be on the phone then.
Yes. Okay,
well, it's going to be a little bit difficult for you to see the graphics then, which is, I think, critical in trying to understand what the mystery is on the Wakefield experiment. Do you have access to the web and can search for stuff?
Yeah, I can see the graphics, yes.
You can see the graphics?
Yes.
Okay, great. So this is the article that was provided. And so the key is, do experimental results mean the end of the road for what has been taught to 14-year-olds throughout the world for 150 years, which is a steady charged capacitor has a static electric field between the two plates? by Ivor Cat. So that is his initial statement of the problem here. So it's not a very complicated experiment. It requires a lot of very high quality oscilloscope. But basically what you've got is a very, very long piece of coaxial cable. And I'm getting a little bit of a echo here, so I'm going to mute some people. And what he's done is that he attached a 9-volt battery on one end, and he's placed a 75 ohm terminating resistor at one end. And this cable is like hundreds of feet long. And he's placed on a oscilloscope probe at like 4 places. One at the beginning, and one at 25%, one at 50%, one at 75%, and one at the end. And so what he does is he charges up this coaxial cable like it was a capacitor by just applying a 9-volt battery. So once it's all charged up, then there's this switch at the end, and it closes the circuit to that 75 ohm resistor so that the charge starts to drain out of that cable. So the 75 ohm resistor is just there to serve as a terminating load, because this is 75 ohm coaxial cable, and the meaning of that is that the coaxial cable itself acts like a 75 ohm resistor to signals, and that's a little bit hard to understand because if you put a meter across a 75 ohm cable, you'll find that the resistance is infinite, but but if you put a signal through it, a radio signal through it, you'll see that it behaves as if it were a 75 ohm resistor. So they can emulate the existence of an infinitely long piece of coaxial cable on the other side with just a 75 ohm resistor. But you can see that the principle is that once you close that switch, then anything that's been stored in that cable can then immediately discharge. So, does anybody have any guesses based on that, or intuitions based on the design of what would you expect to see happen to this experiment when you close the switch? So I'll just start off by saying, well, before you close the switch, everything will read 9 volts, right? And when you close the switch, then things should start reading at like closer to 0 volts at some point. But did anyone have any strong intuitions about what they think might happen, assuming that you don't already know the answer? Anybody want to take a guess at it? No, no one's brave enough to take a guess at it. I was wondering now. So, Bill, are you familiar with the results of this experiment?
Everyone knows, right?
Pardon?
Because everyone knows what is the result here, right? So
I don't know. I'm kind of wondering.
Is yeah, coming up, right?
We already know the result. So,
okay.
I think most of us probably know the result, but the fundamental question is about whether there is what would conventionally be believed an exponential decay or not. I think that might be a question.
Yeah, that might be. Typically you think if we're discharging a capacitor, we would get like this, kind of curve kind of thing. It would go from like 9 to 0, kind of some kind of curve like that. I think that would probably be the expectation.
Well, we know that doesn't happen. So the result of the experiment is that the theory of a charged capacitor is disproved. The prediction, what is predicted, which is an exponential decay curve, does not occur. And so the prediction is not fulfilled in the experiment.
Yeah, so I think that may be, this is maybe why Ivor has put this initial statement here at the top of his article.
Let's talk about the initial statement. because the initial statement is, in my opinion, although Ivor is sort of fixated on this particular language, in my opinion, what he says is misleading. He says a steady charge capacitor. Okay. And he's saying kind of in to the effect that the concept of a steady charge capacitor isn't correct. And that's kind of confusing. And most people, when they hear that, they reject that. This experiment doesn't refute that. That's kind of an issue there.
Yeah, I kind of have an
this
issue with why he makes
shows-
this statement.
Okay, what this experiment shows, okay, let me repeat it again. What this experiment shows is that the behavior is correctly predicted by transmission line theory and is incorrectly predicted by the charged particle, or the theory that something called charge exists that leaks out according to the exponential law. So this particular experiment says that the correct way to make a prediction is not to use the traditional electromagnetic theory taught in physics books, but to use transmission line theory, which is a well-known theory in electrical engineering.
Yeah, well,
Of course. But just getting back to the sort of language used by Ivor Catt, I mean, he states in a number of places that a capacitor is a transmission line. There's absolutely no difference between them. They're synonymous.
That's correct.
Yeah,
That's
well,
what he says.
yeah, exactly. So that's I mean, instead of saying there are certain similarities and you should maybe deal with this using transmission line theory, and there's an analogy with a capacitor and that sort of thing, he says they're identical. So that obviously confuses people, and I think it puts a lot of people off as well.
Well,
me
what
off.
he's saying, I think I said it, I think I tried to say it more precisely. You may want to criticize my statement of it, but I think what he's saying, and he doesn't say it exactly this clearly, but I think what he's saying is that the correct theory is transmission line theory. Okay, so the correct theory is to describe a capacitor according to transmission line theory, not in accordance with the traditional theory of that a capacitor has this thing called charge in it.
Okay, now before we go any further, for David's sake, let's, so we've discussed what the conventional expectation would be, that there would be like this exponential decay curve, but this does not happen. So what happens is that we get a half voltage pulse out of this thing. So it goes steady state, 4 volts, for twice the amount of time it would take for the signal to travel from one end to the other. So let's see. So this is what this trace looks like. It's a little bit hard to figure out what's going on here. So let me see if I can explain it. So I believe the bottom trace here is the one that's of interest. So this this bottom trace is showing flat. That's like at 4 volts. And each of these segments here are 20 milliseconds. So this cable is of a length that it should take, you know, some 60 or 70 milliseconds for a signal to travel from one end of the cable to the end at nearly the speed of light. So instead of seeing, you know, your expectation might be that since it takes 70 milliseconds for a signal to travel the length of the cable, that the signal should only last 70 milliseconds, but it doesn't. It lasts double that. It lasts about 140 milliseconds, and then it dies. So we don't see any kind of exponential decay here at all. It's a step function. And so this is what the signal looks like at the end of the cable. So one of the interesting things, and I believe this was a well-known result, that when you measure a pulse coming out of a coax cable, it's a double-length half voltage signal.
Okay, shall I step in here and kind of clarify what you just said? The transmission line theory says that there is a standing wave on the transmission line. So if the transmission line has a length L, okay, the pulse, there are two waves in the transmission line or one continuous wave, but you can think about it as a standing wave. Does everybody here know what a standing wave is?
Well, you might kind of explain that, because I don't see how a standing wave could apply in this case where it's so dynamic. A standing wave has to have a constantly generated wave to keep it standing. But here we have just suddenly a switch closed, and we have this wildly
you're arguing about the interpretation, Franklin, which is what you normally do, and until somebody's explained to you what the theory is.
Yeah, well, you'll have to justify there being a standing wave in this thing, because I don't see it.
Okay, well, I don't see any point in discussing this any further if you're going to interrupt and object to everything that's said.
Well, that's a discussion. So I'm just saying. Well, it's a standing wave. You asked whether people understand what there's a standing wave. I understand them as being like, I play the violin.
So I don't really see the point in continuing on.
Okay, well that is your right.
May I say something? It was Harry Rieke who was talking, right?
Yes, that's Harry.
Yeah, I guess, I mean, the main point would be actually that on the structures as mentioned, and maybe this one, we actually have, in principle, flow in both directions.
That's what a standing wave is.
Yeah, that might be the main point. And actually, I think I will have opportunity maybe to offer an explanation here. Although I have given it on a couple of occasions during the email discussions, and even prompted Ivor Cat, and she never got back to me.
I think a number of us gave possible explanations.
Yeah, there is.
So we can discuss those, but let's just get through the results of the experiment first.
Why are you, saying that in advance? Well, we are at a good point. So we assume that we have flow in both directions, actually, at least as per Heaviside's theory, right?
Well, I don't see flow in both directions. I mean, I'd like to have that explained to me, because I absolutely don't see it.
It should be much more than just standing waves. That would be also important to keep in mind.
Well, I don't see a standing wave in here. That was my problem. So
don't see it here. Why should you? I mean, you guys, Franklin, you and some other people would like really to see things, to touch it, to touch them, right? Like extreme orthodox positivists, right?
That's me.
Keep still for a while, right? Just lead the conference, right?
I mean, if you have a standing wave, I could understand if you had a radio transmitter at the end of this thing and it was generating a constant oscillating wave. That's total standing wave. But here we have on one end, you just throw in a switch. So it's a pulse.
Well, Franklin, you're objecting until the explanation of this experiment hasn't even been discussed yet. And you're objecting to the explanation when the theory behind it hasn't even been presented. So I think you're just, I don't think that's a role that you should be taking. Okay.
Well, my role is to ask questions, so I ask questions.
Well, I mean,
that's perfectly fair.
Right?
Obviously, Franklin doesn't understand the theory, of the explanation, and doesn't really want to hear about it. So
no, that's not true. I've asked, it's like, okay, explain to me where the standing wave is. And I'd be happy to hear your explanation.
If you don't know what a standing wave is, then I can't help you, Franklin.
I totally know what a standing wave is.
Okay, so. Harry, you should be, honest or prudent enough to admit that it's very difficult to even define the standing wave. Or otherwise, actually, it is, as I said, we here have something more than just standing waves. that are superpositions of two waves traveling from both sides, right? Here we have a process that is going both sides. There should be something more than just traditional, simple kind of standing wave concept, right?
All
So
right. Well,
that
I
view,
think we
that is
understand.
right,
I think
right?
we understand what your position is.
That
Okay.
you could have right, but on the other hand, if we go beyond the conventional, like simplistic kind of conceptualization of the standing wave, then we can explain it. Actually, if we look at the static situation, like static charge, in terms of that kind of two-directional process, flow of energy in that coaxial cable, as could be the case, for example, in a bottle. If we would have a kind of flows in both direction of certain types, some kind of vortexing, both how to say, translational, longitudinal, and transversal, like vortexing, then it presents this very simple explanation, and I have tried to convey it on a couple of occasions. We actually have here, like we have two springs pushed toward each other, along each other, and compressed in some bottle, in some vessel, right? And we just open that vessel, and what happens? That part of that spring that is ready to go to the right just starts going. The other one goes to the left. At the moment when it reaches the end, it reflects and follows this one. So when the first one gets completely out of the bottle, then next one, the second one that was going to the left, just continues the same way. So we have double length and half of the amplitude. And I have offered some kind of block diagram, kind of illustrations in my emails, if anyone of you may remember.
Okay, so that is one possible explanation, that we get a double length signal because we have two signals heading out of this thing, therefore they last twice as long. Right?
Two flows, two flows that go kind of against and across each other, or next to each other, right? And the more we charge this, the more those kind of springs are getting pressed, each for itself and against each other, or whatever. And they just open, and then it starts going out, and orderly going out. First half of it that was kind of moving and spiraling to the right goes out, starts going out. The second one that was prepared, kind of pre-positioned, to go to the left, but of course it has the end of the cable. It has kind of discontinuity, cannot go outside because of the much higher pressure of ether. This is kind of ether dynamical basis for explanation. That one just change direction and start following this one. So if you look at these results, at certain moments, in certain intervals, we have overlapping of both of them, right? But at the output, they are coming out orderly. First one, and immediately that one ends, the second one continues following the suit.
Okay, so that's one explanation. So let's continue on looking at the results of the experiment. So it's simple enough to measure the pulse at the end of the cable when you do this thing. So the unique thing about Wakefield is he put probes at each of the 25, 50, and 75, 100% locations. So let's see. So not only do you have to explain the double length pulse, you have to explain these intermediary pulse. So here at 25% marker, it shows that when the switch is thrown, and this is at the same time scale as the other one, that for a brief while, 20 milliseconds, it remains at the full 8 volts. So as soon as you hit the switch, you're still seeing 8 volts. And then it drops to the 4 volts. and then it goes to 0. And this is before, and the main pulse goes on for a little bit, for another 20 milliseconds after that. So you can see this went like 2.5 divisions. So 2.5 divisions, the signal at the 25% mark has already dropped to 0 at that point. So you got to think of all of these traces happening simultaneously, and all triggered by the closing of the switch event. So instead of seeing a flat 4 volts across the entire 140 milliseconds, we see this 20 milliseconds where it's at full voltage, then it drops to the 4 volts. Then before this line is finished outputting its voltage, it drops to 0 before that. So let's take a look at what happens at the 50% mark. So here we have something which is similar. So now the voltage remains at 8 volts for 40 milliseconds. Then it drops to the 4, just like before, and then like at 20%, it drops to 0 even earlier. So it's a similar kind of curve, but it's like the 4 volt piece of it is getting compressed towards the middle. So that was the 25. And then this is the 50. And then we have another one. This is at the 75% position where it remains at 8 volts for 60 milliseconds. It only stays in the middle 4 volts for about maybe 40 milliseconds, and then drops down to 0. So in the meanwhile, at the end of this chain, it's still putting out 4 volts the whole time. But here at 75, we quickly see that this point is already reading 0. And then finally, at the extreme left, it's 8 volts all the way through the transmission time, the one-way transmission time of about 70 milliseconds. And then it spends no time at 4 volts, immediately drops to 0, and remains 0 all throughout the rest of the event. So you guys understand that when he throws a switch, you got it, this probe out to here, and it's reading 8 volts until the transmission timeline of 70 milliseconds, then immediately drops to 0, and it stays there all the while at the output end. It's outputting 4 volts the whole time, even though at the other opposite end it's already reached 0 right there at about the 70 millisecond line. So who here thinks that's mysterious, or who here thinks they can really explain that behavior?
I don't think it's correct to use the word mysterious. That's incorrect. There's
okay, let's say
about this.
Okay, well, there's nothing mysterious about this. So that is the Wakefield experiment, David. So that is the raw data, and now it's a matter of how do you explain how that happens.
No,
so Slobodan has already provided one possible hypothesis.
Have an hypothesis, and then from an hypothesis, then you construct a theory.
Exactly. So we have Slobodan has suggested something. So Harry, would you like to take a shot at it?
Take a shot at what?
Explaining what this is, so this is not so mysterious.
I'm not explaining anything. There is a theory called transmission line theory, which is a well-developed theory in electrical engineering that, when applied to this particular example, explains it perfectly.
Well, then please explain it to us, because I'm sure a lot of us don't know what transmission theory is.
Okay. In the transmission line theory, the theory is that waves travel down transmission lines in accordance with the laws of electromagnetic theory. And what happens in this particular case is, because you have a transmission line with open ends at both ends, there is what's called a complete reflection at both ends of the transmission line. That creates a standing wave on the transmission line so that you have half of the energy going to the right and half of the energy going to the left, and you have a continuous reflection. Okay, when you close the switch, there is no longer a reflection at the switch end, okay, and the energy that was reflected before the switch was closed travels to the opposite end of the transmission line and reflects. And when the energy completely leaves the transmission line, it is twice as long as you would expect for the transmission line and half of the voltage. And so if you fold that back on top of itself, you get twice the voltage and half the length of the line. So that theory completely explains what happens in the case of this particular experiment.
So let me see if I can figure out. So my question is where the standing wave was. So you're saying that when the 9-volt battery is attached to this line,
Well,
that there is actually a wave going.
You don't know what a standing wave is. Okay.
Well, you're saying that the
I
standing
think
wave.
You should just keep your mouth shut.
No, I'm trying to explain.
Does anybody out there other than Franklin have any questions?
Well, we can do it that way.
Someone else ask a question, to make a point, if I may, that if this explanation is correct, and obviously there are reasons to think that it is possibly adequate, well, then Ivercat is wrong, that conventional theory will actually explain these phenomena. It's just that we've been looking at it from the wrong angle. But he's saying, oh, this is a fundamental reappraisal of the whole basis of electromagnetic theory. He's probably incorrect there, if it can be explained in terms of transmission lines, because it then merely means that if you look at it correctly in terms of transmission lines, reflected voltages, interference and standing waves and all that, you can actually explain it without much difficulty.
Yeah, and I agree with you, and that's part of the difficulty, and people don't really kind of see it. They just sort of ignore what he's saying, and that's the easiest way to dismiss it. I think you've kind of expressed it fairly well. The issue is, though, that there is this disconnect between the primary assumptions of the traditional electromagnetic theory and what the Wakefield experiment tends to show. The traditional theory would say something like, this transmission line is full of things called electrons, and these electrons are called charge. And based on that theory, which basically gives you a relationship between the packing of the electrons in the transmission line and the voltage on the transmission line, that theory predicts an exponential decay, which is not observed.
Well, let's talk about that. So Harry, do you think that this disproves the flow of current as electrons hypothesis? Is that what you're saying? I mean, that seemed to be a more key thing to Ivercat, because reading through this article, I really don't get that sense, actually.
So I was just curious about, this is David, about how Ivercat mentioned something to the effect that he perceives it as a light transmission. In other words, everything's happening at the speed of light as opposed to the traditional flow of electrons. And so, and also too, is there a way I can get a copy of this particular article? I haven't seen this one yet.
Oh, well, I suppose I could email it to you. Yeah, I've got it saved on my computer.
Yep.
If you go to the Ivercat website, you should be able to get this. The problem with that is, of course, that you know, there's so much stuff there, it's hard to figure out what's what.
Yes, that's true.
Do you have his email address?
Who has whose email address?
Do you have Ivor Cat's email address? You might
Yes,
email him.
yes. I emailed him, but I haven't got a response yet.
Okay. Do you have my email address? kc3mx@yahoo.com. I can send you a copy of this.
Yeah, that'd be great.
Well, send me an email.
Can you repeat it again?
Well, I'll send you a copy.
Franklin's going to send you one.
Yeah,
Okay,
because I
great.
got your email address, and I can just send you this.
Okay, thank you.
Also, if you go to CNPS, whatever the site is, I forget the. Are you familiar with the CNPS website?
Yes, I am.
If you go there and if you go /Harry Ricker, HARRYRICKER, that's in little letters, and then there's a backstroke. Okay, so you go to CNPS site, okay, .org site, /Harry Ricker, and there's a discussion of this Wakefield experiment on there.
Okay, I'll do that. That's Harry Ricker, as in RICHKER.
RICK.
RICK.
With regard to your first point there, I think that Ivor Cat is more or less using the concept which was introduced by Heaviside, that conventional current in any sort of wire is not due to flow of electrons, but is basically an electromagnetic wave traveling in the environs around the cable.
Sure.
So he's basically, he talks about a conductor as being an obstructor rather than, or a facilitator, depending upon which way you look at it, rather than a conventional flow, like a pipe, for example, with water coming through it, a conduit for water to go through, or a fluid or electricity. Now, personally, I think it's actually probably a combination of both. I don't dismiss the Heaviside idea. In actual fact, I use it. But I think Cat uses it to the exclusion of the conventional view. And I think possibly that's a mistake.
I think you're right about that. And this is Bill Lucas. But what I found happened was after Maxwell got the empirical equations of electrodynamics together and solved it with quaternions, people didn't like quaternions, and so Oliver Heaviside redid it after Maxwell died in terms of vectors. But when he did that, he did not use the complete set of the empirical equations of electrodynamics. He used a partial set, and then he used certain transformations to get rid of some terms. And one of the terms he got rid of was the longitudinal radiation. And longitudinal radiation is made in capacitors and these conducting cables that you see there. And so that is being ignored. It is not measured by these instruments. And but there are instruments available on the internet now that can measure it. And one is called the Experimental Life Energy Meter. And life energy uses longitudinal radiation. And so you can measure the longitudinal radiation coming off of any experiment you want with that. And it's very sensitive. It doesn't require any wires. And so that's one thing you can do. But so the question is, what is the proper interpretation of electrodynamics? Is it the complete set of the empirical equations or a partial set? And Isaac Newton said, you should always use the complete set, not the partial set, because you only get a partial solution to your problem. So that's the question is, what Ian said is he's basically saying indirectly that you need both types. And it turns out that the transmission line is explained more by longitudinal than it is by the transverse wave. So My work that I've been publishing seems to explain all these types of experiments, and that's unusual that we would have made such an error. But here's something that you'll never hear. There is a reason why this was done, and it's a political reason. And the reason was there was, starting in the 1840s, a major spiritual reformation. It's called the Second Great Awakening. And there was a lot of resistance to that. And the idea was promoted by those who were resisting it to use science to combat religion. And so what you'll find is all the scientific theories developed after 1840 or 50 or whatever, up till the present, they changed the scientific method to take the role of logic out so they could get the conclusions they wanted in order to combat religion. And if you correct that, you'll get better science and put logic back in there. See, these theories are not falsified because they have an assumption that's not true. And the work of Heaviside has assumptions that are not true. And so one needs to look at that. And you'll find if you look at quantum mechanics, the theory of the atom, the theory of the nucleus, the theory of elementary particles, relativity theory, all of them have assumptions that are known not to be true. So what they did is they changed the scientific method so you don't falsify a theory based on ideas that are not true. And you only say, well, if they don't predict the experimental results, if the theory doesn't predict it, it can be falsified by that. But we don't do that.
Well, can I ask you a question at this point?
Sure.
Since we're talking about falsification, which seems to, there are a couple of other forums where this question has come up. The concept of falsification, everybody sort of gives lip service to a scientific theory has to be falsifiable, but that's another story. Do you or do you not believe that this Wakefield experiment falsifies the traditional electromagnetic theory?
It falsifies the false electromagnetic theory, yes.
Good.
Because we know it's false, because we know that what Heaviside did was not what you're supposed to do. You're not supposed to throw away terms from your electromagnetic empirical force laws. You're not to throw away some of the empirical laws saying, I don't like that one. That's not the way to do science. And so, for instance, Lenz's law was never used.
All right.
And Lenz's law, when he put it in, guess what you get? The results of special and general relativity. But you also are able to handle dark matter and dark energy. They're just normal electromagnetic phenomena. And so many things were missed by doing that. But they did it for political, religious reasons. They didn't do it because they wanted to get correct science. And it's just amazing to see that. So you have to go into the personal lives of many of these people in order to see what they were doing. And it's so as scientists, we have the opportunity to point out what has been happening. But most scientists won't do that. When I have done it, the National Science Foundation and the Department of Energy in the United States made sure I was blackballed and could never be hired in the physics community again because they did not want that to be known. And so you got to be careful. If you work at one of these places that is controlled, you will have the same experience. And we had in the Natural Philosophy Alliance, we used to have hundreds of people who had experienced the same thing I experienced. In other words, they lost their job in a university because they pointed out that the scientific method they were using was not valid.
Bill, can I comment a little bit on this?
Sure.
I was watching TV about a week ago, and a guy was on there, and this is one of these pop science shows. And he made the statement that, he believed in the laws of physics and that the objective of science was to, what he was doing in astrophysics was he was applying the laws of physics to the universe. And he thought that was real exciting because, he was interested in mathematics, blah, blah, blah. And it suddenly struck me that what they're doing is they're applying what they think the laws of physics are. And they're so convinced that they know what they are that they don't want to hear any alternative ideas that don't conform to their set of laws that they believe in. And that sounds to me kind of like what you're saying. In other words, if you don't accept all the laws of physics that they set down in the physics books, and you think, well, maybe there's, I kind of disagree with how all those laws have been written down and how they're being interpreted, then you can't practice physics.
Well, it's a little more straightforward than that in some sense. If you were to look at the empirical laws of electrodynamics in the days of Maxwell, you would find there were 6. How many did Oliver Heaviside use? 4. Why didn't he use the other 2? Because they didn't promote
Well, Bill, I sort of disagree with you on this point. Oliver Heaviside, basically, his primary claim to fame was he used differential equations to calculate motion of electricity on transmission lines, primarily on telegraph lines. And one could probably argue that he didn't really need the Lenz's law for that. And maybe it was a mistake that he didn't use it, but that was pretty successful in developing, that was really pretty revolutionary and forward thinking at the time.
Well, let me ask you a question. If I have 6 unknowns and 6 equations, am I going to get a valid solution if I throw away 2 of those equations and take the terms that the unknowns that they deal with and remove them from the remaining 4 equations? And the answer is you may be able to predict some things, but you're not going to have a true theory.
Well, I'm not sure that, Harry asked whether you thought that current is a flow of electrons. So that was against Heaviside's ideas. So I've been listening to this, but I'm not sure that I got an answer to that question.
Okay, where did the idea come from that the electron was a charged particle?
From the Greeks, wasn't it?
Well, that was Stoney in 1890 or something like that. Basically, Heaviside, and a lot of this work was done before there was any notion of an electron or anything like that.
What is the history of the electron anyway? So when did we think
the electron is called a magnetic molecule by Ampere and Faraday?
Okay, so Faraday and Ampere started this idea that, because it's not obvious that electricity is in fact the flow of these particles called electrons. So what is the history of that?
No,
so you're saying that
Stoney measured the charge on an elementary particle, which he called the electron after the Greek word for amber, by the electrolysis of water, and he got a value of 10 to the minus 20. It wasn't called coulombs in those days. I think it was called amperes. It was just a factor of time in it, but it's a tenth of the currently accepted value. And then, of course, it was at the turn of the century that J.J. Thomson actually found it experimentally. But it was Stoney who actually itemized this elementary charge.
And that was pretty late in the 19th century.
Yeah, as you said, I think it was the 1880s, Harry. Yes.
So this whole idea of electricity being electrons is a relatively late comer.
Correct.
Well, also, let's stop for a moment. where did the idea that charge was a physical substance come from? The empirical laws that were done, they had to try and describe what was being observed mathematically, and so they put a Q in for the charge. But what was the charge? If I were to look at something like a, cyclone or a tornado, I could say, oh yeah, it's this the little trough that comes down, to the ground, and it's so big, and I'm going to call that the charge. But that's not what a tornado is. A tornado is really big. That's a mathematical approximation. And so what we're doing is we're concentrating on a mathematical approximation because we didn't know how to explain these empirical laws in terms of uh, things like twirling fields and things of that sort. But
So I'm still not quite sure if I understand whether there are actually particles heading out of the end of this coaxial cable or not. I mean, that's the question we're asking here.
Arthur Compton, who won a Nobel Prize for this, showed that there was a wavelength associated with an electron. Well, if it's a particle, it can't have a wavelength. If it's a clunk, a sphere of charge, it can't have a wavelength. And then what did his last graduate student do? Winston Bostick. He made these particles, or if you want to call them electrons, out of the field. So the field is the fundamental thing, and it's a mathematical approximation to talk about a charge. But what are we doing in this Wakefield experiment? We're trying to imagine things in terms of charge. But when you use a longitudinal detector, you discover, oh, it isn't a charge, it's a field. I can see it. And so I can measure it. But you don't see anyone using a longitudinal meter on these experiments, do you? No, because they don't want to admit that that's what's going on. And so there's a lot of factors going on here. And if you've never been exposed to them, you've got to open your eyes so you can see.
Well, I don't know. I'm still trying to answer that question of whether, but it kind of sounds like you're saying that there aren't electrons to be flowing out because there's something else. Is that more your point?
I'm saying that electrons do not have a finite size. They extend to great distances. They're like a hurricane or a tornado. And there's a funnel, that you can see and you can measure with the various experiments, but it doesn't tell you the whole story. And you're making mathematical approximations, which is what Oliver Heaviside did, and other people followed in that path. And we're now that we've done the experiments that Arthur Compton and his last graduate student has done, and they've been repeated in many places, we know that those approximations we made were wrong. And so we have to use a proper interpretation of the empirical laws. So where we have a Q or an E or something like that in those equations, we now know that that represents a standing wave in the electromagnetic field. And so, and it has the funnel, if you want to talk about it that way, has a finite size, but that's not the whole thing. It extends, and we don't need an ether because the fields extend to great distances, and there is a tensile strength in the electromagnetic field, and that was measured by Hooper. And so people did not like the work of Hooper because it falsified their theories, so they tried to push him off to the side. But he actually measured 13 different properties of electric and magnetic fields. Each
Well, it sounds like you're defining, what an electron is. That's something, different, and
we
that's fine.
what it
But
is.
I think the question is fundamentally when you have a battery and there is a current flowing through it and it's creating magnetic fields and whatnot, is that a flow of electrons, however you imagine them to be?
No,
If you have a transmission,
That's kind of an ambiguous circular question.
if you have a transmission line and you have an antenna, you'll find you have problems with that interpretation. You can't explain both with the same interpretation.
Yeah, that's
Yeah,
a
but I'm
good
just trying to
point,
wonder
Bill.
why when I light my light bulb up with the battery, I mean, what's going on there? Is it a flow of particles of whatever type you want, or is it not?
It's a flow of
yes, it is, but of very, very small particles. Like,
Well, yes, it could be flow of very small particles. That's one way
that
to say it.
analogy with the tornado, right? Consider kind of three-dimensional vortex consisted of flow of some particles, some molecules, some atoms. You can go down there, So within the electron, as a toroidal vortex formation, we have actually flow of certain particles, which are much smaller than that particular size. And the movement around the equator, like ring-like movement, is actually electric field. The other one that goes like torally, like kind of meridianally, is magnetic field. I mean,
But-
what's the problem? Actually, one has to consider the ether substrate, where actually the field. You have to.
I still don't think I'm getting an answer here.
Spontaneously or being induced or whatever, So, I mean, there is no flow of electrons in the conductor. There is only just a certain inclination, alignment of electron formations along the line of the electric field applied. And then those movements actually induce the movement around the conductor. So we have flow of ether particles, both along the conductor and around the conductor, outside or inside, when we are talking here about the coaxial cable. So
yeah, well, that's another alternative.
Just one more thing, please. Talking about standing waves. So we have to consider, actually, you mentioned electron extending wave. So, okay, I mean, conditionally we can accept that. So here we can consider kind of structure within this coaxial cable that is kind of standing wave or kind of three-dimensional flow of those particles that are very much smaller than electrons themselves or protons or whatever, right? And actually, that flow is structured in a particular way to go both directions, go rotationally, and then just when you open the bottle, they go out orderly. I mean, what's the problem there?
Oh, but by the way, for David, if you can see the chat, I put the link to the Wakefield paper in the chat. So if you can see that, you can get that. Now, I also see in the chat there's some comments from M. Faraday. So I presume we have Michael Faraday with us, and perhaps he has. Would you like to comment? Or you would like to continue lurking here, Michael?
He's
I'd
got
like to
two
comment
R's.
a bit on what
Presumably
Slobodan
a different
said.
person. He's spelling his name with two R's, so presumably
Yeah,
he's
it's not exactly, but yeah, I think we know who he's trying to. I'd like to get some other people in the conversation here besides
Sorry
me.
to come in again, but just as regards your point about the wire, say an electric light bulb obtaining electricity, the electrons themselves, if you can conceive that they are flowing through the wire, they're not actually the conductors of the electricity per se, because they're drifting at a very, very slow speed through the wire. The electric current is almost instantaneous. I mean, I maintain actually it's orders of magnitude greater than the speed of light, but we can talk about that at some other time. But basically, we've looked at it perhaps in the sense that you could conceive a long tube with little billiard balls which are stationed right beside each other, and if you move one at one end, you put another billiard ball in, well, then the one at the other end will almost instantaneously fall out. So you should conceive of the electrons as being sort of like unified through their fields throughout the cable and not being the individual conductors of electricity. Nor should you consider positive holes going in the other direction to be such. But by the way, on the Heaviside business, Heaviside, of course, was a practical man, and he introduced a lot of concepts which made things easier. I mean, it's much easier to manipulate Maxwell's equations with his terminology, his vector terminology, than it is the original quaternions. But he did do things which perhaps mathematicians, pure mathematicians, might consider to be totally rigorous. Like he'd introduce the term P for the derivative and then treat it as if it were just an algebraic quantity which could be divided and multiplied and squared and all that. Now, he got some good practical results, but there may have been some anomalies from what he did. And with regard to the Maxwell equations, I think Bill talked about Lenz's law, and I've forgotten what the other one, and these probably were neglected. But I thought that the two divergence equations were not actually independent of the curl equations and could be derived therefrom. So, I'm just questioning whether he left everything out. He neglected some things, perhaps.
Well, one of the things that
Maxwell did wrongly, he actually did not consider non-zero divergence of D and B. You know, that's the biggest, how say, deficiency of those equations. You know, once you get the non-zero divergences, the divergences outside of the source, like for example Q of certain charge or whatever, or magnetic charge even, then you get the whole the complete or say that wave equation, right? Laplace equation, right? And then you have both longitudinal and transversal perturbations or whatever mechanism, and then you are fine. Then with there, you actually see here that ether structure get formed by being induced by certain just repositioning of structural electrons inside the conductor, and everything can really become clear. I mean, very how to say, plainly explained.
I don't know. None of this sounds very plain to me.
But that's maybe talking about different terminology or whatever. Okay, I said, if you consider charge as kind of, say, conditionally, that kind of standing wave, right? Actually, standing wave is kind of a structure. Maybe have some flow, right? We are just fine then, right? We cannot expect, and it's not possible, as many people here stated, that electron, by moving within the conductor, create magnetic field. No.
Okay.
They're partially moving, but main effect is just turning around, aligning to a certain extent along the applied electric field, and then they induce the movement, kind of complementary movements in the surroundings, ether, and then get structured so that you have particular kind of flow along the conductor and around the conductor, combined, composite, you know. When you look closer into it, you will see everything. Everything becomes unclear.
Okay, so I want to get some other opinions and give other opportunities for people to express their opinions.
Kind of to find common ground here, and I see many people. Lucas, this guy who was talking, I don't know what his name was. So you know, we are quite close there, right?
So it's like for example, David, you asked this original question about the Wakefield experiments. Are you drawing any conclusions from this discussion here? I'm going to unmute you. See if I can do that. Are you there, David? Because if you guys don't start chipping up, I'm going to start calling names in the class here. So
where does the vector potential fit into all this?
I have no idea. What does vector potential have? What is vector potential?
Vector potential is a non-physical quantity which was used instead of the energy potential because it gave the results they wanted politically, not the results that were needed experimentally. And when you use the energy potential with the complete set of the empirical equations of electrodynamics, you get the force laws for electrodynamics in terms of not just the radial and velocity terms, but you also get the acceleration and the radiation reaction, the dAdt terms, which go beyond special relativity and general relativity. In other words, we missed all that because we had political goals. And that's what, if we just used the energy potential the same way that Isaac Newton had, we would have done much better in electrodynamics. And I published that. It's in my book, The Universal Force, Volume 1, if you want to know what it is.
Isn't the curl of vector potential the magnetic field?
Pardon?
Isn't the curl of the vector potential the magnetic field?
Yes.
So isn't that imply some kind of physical reality to it?
Not necessarily. Why would you think that?
I'm just asking at this point. I don't understand it myself.
It doesn't get all the terms in the magnetic field. It misses some.
I mean, Jim, do you think that this experiment can be explained by conventional current explanations that, current is a flow of physical electrons or not?
I'm sorry. I have to correct you here. Okay? I have to correct you here. This experiment is an experiment designed to test a particular prediction made by Ivor Catt, who has a theory based on transmission lines. Okay, so what Ivor Catt did is he says, I have a theory, this is a scientific method, I have a theory, and now I'm going to do an experiment that demonstrates that my theory is correct. That's what this experiment does. You started off by asking, well, does anybody else have another explanation of this experiment? That's not the scientific method. So let's try to use the scientific method if we can, okay?
Well, you got me confused because I always thought the scientific method was to take observations
Harry.
and fit hypotheses to them.
Okay.
And anyone is free to fit as many hypotheses on any particular experiment as they want, especially if someone wishes to dispute someone else's
hypothesis.
You're just
confusing the issue, Franklin. Please don't do that.
Harry?
No, that's not confusing the issue. That is the issue.
Okay, Harry, don't you think that my addendum here to consider the charge itself as a standing wave conditionally fits into your view or not?
Yes, I do. I understand what you're saying. And quite frankly, I think your interpretation is not really that significantly different than what Ivor is saying.
Oh, it is not.
And,
but when you have standing wave, don't you need boundaries?
Correct.
How can you have standing waves that don't have boundaries?
Reflection at the end.
You have here boundaries. You have a very high pressure of ether around this structure.
I'm not talking about this by itself. I'm talking about in general. You've got electron beams. There's no boundaries on an electron.
The electron as static wave is actually kind of a structure of certain form, consisting of movement of certain particles, inscribing that shape, that form. We cannot think of something like static, something like, we define some geometry and say we have a charge. No, that form is actually formed like that famous smoker ring, That's this very basic shape, and it is created by those particles of smoke. Okay, when tobacco burns, right? What turns out those molecules, right? There and down there at the atomic level, electron level, we have much smaller scale, and those particles create the fluid particles for formation of those particular forms. You know, saying just static wave is pretty much kind of, you know, how to say, artificial and kind of, or saying that electron is standing wave. I mean, we can consider, tell me it that way, but we have to look inside, beyond that. What is the basis of it? What physically it is? And we have to go to ether. No way, Adam.
Well, I would probably.
So when I say here, you know, inside the coaxial cable, by influence of this battery, you know, there's potential difference. You have the structuring, you know, and that structuring reduces the pressure because that movement of those subatomic particles that form kind of pressure of temperature or whatever, they actually turn into the organized movement within certain structures, and the pressure reduces, and the outside pressure is much higher, and it doesn't allow for this content to get out. Once we attach another cable or this resistor, we allow for that pressure to be kind of removed on one side. On the other side, still that pressure there. And that pressure, you know how big it is? 10 to 36 Newton per meter square.
Okay, so I kind of take issue with a lot of the things that are being said here. Things about there being standing waves and things about electrons being made out of standing waves. And I just have a tremendous amount of skepticism for anything.
Well, you can't take issue with the hypothesis, okay? There is a hypothesis. What you have here is a theory, okay? A theory based on well-established, well-known, very much experimentally verified knowledge of electromagnetic theory, okay? And an experiment, and there is a theory based on transmission line theory. There is a theory, that's the theory, that's a well-established theory. Okay, and then what Ivercat did was, hold on. What Ivercat did was he took this transmission line theory and he made an hypothesis which has to do with the heaviside energy current concept. And he said, well, I suppose that in this case of a, quote, static capacitor, we don't really have a static capacitor. What we have is a standing wave. Okay, and so we can apply transmission line theory. We apply transmission line theory. We get predictions based on that transmission line theory, and then we do an experiment and we compare the results of our experiment to the predictions of the theory that we have. That's called the scientific method. Okay, and in this case, the results of the experiment come out to be exactly what is predicted on the basis of the transmission line theory. That's all there is here.
Okay, that's good and well. Now I'm obviously a positive here. So I'm going to represent the.
So you're not going to use the scientific method. You're just going to say that the hypothesis is wrong, and I disagree.
No, I'm just going to say I have a different hypothesis.
This experiment doesn't prove what it supposedly proves. So
and that is the scientific method.
No, you're not using the scientific method. You never do.
No, I am using the scientific. I believe that this experiment can be explained with conventional current as an electron theory. So if I can, I am free to explain any physical experiment, and it's a judgment call amongst everyone as to whether those things are correct. So this is what I'm going to do. So I'm going to attempt to represent the conventional wisdom in this case, that an electron is in fact this little particle that carries charge, which flows through wires. That is the conventional view. So I'm going to give my explanation for why that is, and the only thing I ask is that you not interrupt me until I say,
well, you
can't. Questions?
First off, you're doing it incorrectly. You can't. What you're doing is you're making an ad hoc hypothesis. Okay, that's not how it works.
Yes, well, this
Okay,
is a
you're doing it
hypothesis.
backwards. You're saying, oh, I can explain this experiment. I can explain this experiment. That's not scientific method. Okay?
That is totally
Either
the scientific
accept
method.
that
What you
this
just said
experiment.
doesn't make any sense.
No. That's just your opinion. That's
I
not
mean,
science. It's just your
everything
opinion.
is our. I mean, this is the way you typically do science. Is that we
No, the
have
way
an
I
experiment.
explained it
We
is how we
observe
do
something.
science. The way you explained it is nonsense.
Well, I have my opportunity here to explain it. So I'm going to take off my moderator hat and
Why
I'm
are
going
you
to give an
explaining it?
explanation
Why do you think you need to explain it?
to show that this can be explained without resorting to standing waves, without resorting to transmission theory, without resorting to Heaviside, that this can be
So you're
explained
going to
much
present a
simpler.
theory. So you're going to
Yes,
present a
I'm going to
theory.
present a theory, absolutely. So the only thing I ask is that you not interrupt until I say, are there questions? Can you agree to that?
No, because you're going to present a bunch of ridiculous, ludicrous hypotheses that are not physical. Okay, and I don't really see the whole point of this exercise.
The point of this exercise is so that the other people who are watching and listening who might be interested in an explanation would be able to get one without constant interruption.
But you're not going to present an explanation. You're going to present a bunch of silly, hypothetical nonsense. Okay,
Well,
which is
that
what you
is
did.
the opinion of, I mean, I may do that, but that's fine. I just ask that you
I'm not really sure
respect
that this
my
is
time.
really the point of this forum. If you want to make a presentation where you present an alternative explanation of this experiment, then you can set up a forum and we can discuss that. Okay.
That is this forum, Harry. That is exactly
so
this
what
forum.
is your point? What is really your point? You
My
are
point is that this can be
yeah.
explained
Wait a
by
minute,
conventional
wait a
theory.
minute. You're refusing to accept the concept of standing wave, which is in every engineering textbook. Okay, so you say that's wrong. Why
That's
do
wrong.
you say so? You
That
say
is
so.
wrong.
Now, I see
Because,
no reason to listen to you further.
well, you don't have to listen to me, but I'm just asking that you respect, as I speak, that you not interrupt. That's all I'm asking. Just be quiet for about like 3 minutes.
What authorizes you to present your silly ideas? Just because you're
I
the
authorize me to make my
forum?
silly ideas. Everybody is authorized. Carrie, can you just like be quiet for 3 minutes while I give my explanation? That's all I'm asking.
Go
Now,
ahead.
as moderator, I can actually mute you. So,
Well,
I
go
mean,
ahead
I don't
and
have
mute
to.
me. The bottom line is you don't understand something that's fundamental to electrical engineering and you're saying it's wrong. And I don't see what entitles you to say that.
We are entitled. This is a science chat. This is open. This is not.
You're not in.
This is
How are you entitled to deny the fundamentals of what's taught in engineering schools?
I'm going to use everything that is taught in engineering schools, from basic electronics. Now, if you would just be quiet for just 3 minutes, I can explain it, okay? Because this is my claim, that this signal trace can be easily explained by conventional electronic theory. Okay, so I'm starting my explanation now, so just hold your questions or objections until the end. I assure you, you will be able to get those objections in, okay? Just don't interrupt, okay? So the things we have to explain in the Wakefield experiment is, number one, why is it we get a half voltage pulse, and why does it last twice as long? Now, in regular electronics, what we have here in this experiment is something called a voltage divider. So this little 75 ohm resistor here is not an innocuous part of this experiment. This, when combined with this transmission line over here, which is also effectively a 75 ohm resistor, creates a voltage divider. See, now this is very conventional, proven. If you tap out the middle of two resistors of the same value, you get half the voltage. So this is why we get 4 volts out of this experiment, because all you're doing is producing a voltage divider. Now, if you consider the standard, V equals IR kind of considerations, that if we reduce the voltage by half, then the amount of time it will take for any fixed amount of current to flow through a wire will double if you reduce the voltage by half. So therefore, we would fully expect that if somehow the voltage is coming out of here at half voltage, that it would take twice as long for it to just leak out, right? And my prediction would be that if you change the value of this resistor, that would directly control the value of the voltage coming out of this experiment according to voltage divider law. So I don't consider what's coming out of the end of this to be really any mystery. That is just straight conventional electronics and formulas by voltage divider law. So now we have to explain what is going on at these various other points. So let's just start at the very end where it's registering 8 volts right up until the time that the signal transmission time, in which case it heads to 0. So conventional theory says that this wire is filled with these physical little electrons, the full length of this thing. So I'm going to say, let's just imagine all of those as being like marbles that completely fill this tube. Okay, so pretend you've got marbles in this tube, and that's what we conventionally think of as electrons. And when we throw this switch, those marbles start rolling out the end of this tube, right? So that's what happens when we start closing this switch and the marbles start flowing back through the current here. So that is conventional electron theory. So why does it take so long for this to suddenly go to 0? So the thing is that if you imagine that this was moving marbles, that they can't all move out of the tube at once. That they've got to start moving from here, and then slowly, you start seeing a flow of marbles coming out of the tube. And meanwhile, over here at the end really doesn't see anything while these marbles are flowing out. So they're going to start flowing out and they're going to be solid until the transmission time, which it hits the end. And then all the marbles will be gone, and all marbles being gone meaning 0 volts. So this is why it takes the transmission time. So the speed of light, it takes the speed of light for this thing to kind of empty out to this point. So when it does, there are no marbles here, so we suddenly see the voltage drop to 0 at the transmission time. So it takes the speed of light for this trail of marbles to finally reach here. And that's why we get the sudden drop from the 8 to the 0. Now, if we consider some parts in the middle, like the 75% thing, once again, we have the marbles flowing out until it reaches this point. But at this point, we still have marbles heading out from the segment here. So this is like still being attached to the battery. So we're still getting a voltage divider effect. So we see the 4 volts. But as soon as that marble, the last marble, rolls from here to here, then we are at 0 again. So that explains why that is like that. Now the rest of these traces are very similar in that you see that as the marbles flow out, that it won't drop until it reaches this point. It continues for 4 volts as long as there's still marbles flowing back here, because remember, there's still marbles that started all the way back here, which still have to flow all the way past this point. And while it's doing that, you get the voltage divider 4 volts. And then when the last marble has gone past that point, we hit 0. And then finally, it's exactly the same argument on the 25%. And then finally, we see the final result where when the last marble finally exits the tube that used to be way over here, as soon as they go, finally gets out, and it can only get out at like, half the rate it might normally get out because of the voltage divider. Then we see the sudden drop to 0. So that is my conventional explanation as electrons as being little particles that flow out, and I explained it basically with this marble analogy. So that is my conventional explanation. So now, are there questions? Here's your opportunity to beat me up, Harry. Go ahead.
You're saying that electrons are marbles. That's absurd.
Yes, I am exactly saying electrons are marbles.
There's nothing really to comment on other than it's just a fantasy that you made up. Not really science. It's not. I mean, there's nothing to comment on. It's just something.
I mean, there's nothing wrong with electrons as marbles. Like I said, this is how people conventionally think of electrons, as particles, as flowing through the wires. I mean, they might as well be marbles.
That's ridiculous.
The marble interpretation did not explain the atom.
Why do I have to explain the atom? I'm explaining the results of the Wakefield experiment here.
That's where we first started working with electrons. We learned the properties of electrons, and the Bohr model could only make predictions for hydrogen. It couldn't do any other atom.
I'm not quite sure what the relevancy here is. Because electrons definitely exist outside of atoms. I mean, we can form beams of them, so therefore we can talk about them independently from atoms.
A beam of electrons, the higher the energy, the smaller the electron.
And in this case, that really doesn't matter. The size doesn't matter. I mean,
if you had marbles,
the electrons could be as big as an inch, and flowing through a tube that's 3 inches, it wouldn't matter.
The physical particles do not change their size. When you shoot a bullet out of a gun, it's still of the same size as it was before you shot it. And
I mean, I appreciate that, but it's not relevant to my explanation of the Wakefield experiment.
It is. Because you're talking about things that are occurring on a microscopic basis inside the cable.
Yes, and I am saying that on a microscopic cable statement, there are like millions of these electrons which are flowing out. And as an analogy, you know, I mean, I'm not saying that electrons are marbles, you know, but as an analogy, you can see that they start out packed in this tube, and that they flow out of this tube. That is the conventional view of the electron, and nothing you say about its relevancy to atoms or the size, none of that really affects my explanation any.
Well, you don't explain why the voltage forces the electrons out of your so-called quote tube. And under the conventional theory, you have charge between the plates. The charge between the plates is related to voltage according to the capacitance. And so you have a charge versus voltage in relationship to the capacitance. Okay, that's a law of physics. The conventional view says that we take that as the charge, okay, is forced out of between the plates. In other words, the charge is forced to flow into the resistor by the voltage across the plates. As that charge goes into the resistor and disappears, the voltage declines, which reduces the force on the charge inside the plates, and you get an exponential decay. That's the traditional theory. Your theory doesn't take into account why these balls are moving around because you don't deal with the issue of the voltage.
No, a conventional theory, the voltage is analogous to, say, the pressure. You don't know
what you're talking about, Franklin, please.
Yes, I do know what I'm talking about.
No, you don't.
The voltage
here's
is
another thing. Another thing. You make this hypothesis here that you have a voltage divider between the transmission line and the resistor. That's not a voltage divider. Sorry.
No, look up voltage divider. Whenever you're tapping between two resistors of the same value, that is a voltage divider. That is an undisputable fact.
Line is not a resistor, please.
Well, then why is it they call this a coaxial cable a 75 ohm cable?
Because the ratio of voltage to current on the transmission line is equal to 75 ohms.
Which means what? What is that resistance there? I mean, 75 ohms
There's no
is a
resistance in a
It's-
transmission line other than
it's,
the loss in the line.
I think
You
what's
don't know what
what's
you're talking
represented.
about. You don't know anything.
I think what's represented on the transmission line is that is expressed in ohms as impedance. It's not standard linear resistance. It's an impedance value for signal.
Yes, and what does that impedance value mean physically?
It's the ratio.
It's
of the
a
voltage
combination.
to current.
It's a combination of resistance, capacitance, and inductance.
Yes, to my understanding, it is the equivalent resistance that you get when a signal is traveling through the line.
No. It is the ratio of voltage to current.
Yes, there's a resistance in there. So when you have
That's not
the current
resistance.
flowing,
That's
it
not
does
resistance.
not flow. It is a resistance. It's not a real resistance.
No. You don't even know the fundamentals of electricity.
No, I am positive on this.
So what
The thing is that if you run a signal, an oscillating signal through a 75 ohm cable, what you will find is that if you calculate the voltage versus the current, that it's the same thing as if you had put a 75 ohm resistor there. So you can replace the entire 75 ohm cable with just a 75 ohm resistor. That is what a terminating resistor does. And that's why it has the value of 75 ohms, because it basically, within an oscillating circuit, does the same thing as a resistor.
No, it doesn't. It's not a resistor.
It's not a resistor, but it kind of acts
is
like
not
one,
a
two varying current
Resistor
and
absorbs the power. A transmission line does not absorb the power. It transmits the power.
I'm also a proponent.
of this experiment, I believe, because we do have moving voltages and currents. It is putting up. I mean, it's not letting the current flow infinitely fast because of all these inductive effects and things like. It cannot flow out with like the same thing as a bare copper wire. It has something which is resisting the flow of current. So that's typically expressed by resistance, and that is it. But the thing is, the point is that I'm claiming that the 4 volts. Why is it exactly 4 volts? Because there is a voltage divider there, and you could prove that by changing the termination resistor. If you change the termination resistor, you should be able to predict the voltage, and if it really is a voltage divider, then you could easily change the resistor and get different voltages. You could predict how long it would last and what the voltage would be if it's a voltage divider.
The point with the resistor here is a matched resistor, right? It emulates the
It's been done. Wakefield did that. You just didn't look at the rest of what he did.
Right. I just have one other point, if I may, Franklin. I think your hypothesis conceives of the flow through the wire as being effectively conventional electron flow. So I'm wondering, have you dismissed altogether the Heaviside cat type of electromagnetic field transmission around the cable? Excuse me. And if so, how is it that you're attributing a speed roughly that of light to the flow of electrons in the cable?
Well, first of all, probably I would say they're wrong. I can't really express it any more than that. And I would explain specifically, Wakefield and Heaviside. Any notion that electrons are not the flow of electrons, I believe, is just fundamentally wrong. But that's my opinion.
Franklin, could you please, put the screen to my disposal, just to show one diagram, just
a moment. I'm still answering Ian's, and then I will give you permission to share your screen. So, and Ian, you asked
about the speed,
why is it the speed of light is in there, and that's because the because what we're talking about, it's like you have a pipe that's filled with pressurized water. And I would believe that if you did this experiment, it's the same experiment, but did it with a pipe full of pressurized water, and you set it up the same way, you would get the same results. And the thing is that, so you have a pipe with pressurized water, you open up one end. Now that pressure is not going to decrease instantaneously. It's going to take some time for the wave go from the left-hand side of the pipe to, the right-hand side to the left-hand side of the pipe. That would be the transmission speed of basically a wave, because, there's not a lot of particles heading out of this thing. It's very small still. But as things start exiting and start leaving space, then that is basically like a wave, and every medium has a wave transmission speed. And so the fastest that that wave can get to the other side here, it would be the speed of light. So we see this wave reaching the end of this coaxial cable at the like 70 millisecond speed, and that just corresponds to the speed of that transmission wave, which is very close to the speed of light. So that's how I would explain that. So does that answer your question?
Give me the control of the speed.
More or less it does, but just one point. The speed within the cable is dependent upon the inductance per unit length and the capacitance per unit length. So by adjusting those parameters, you could actually exceed that in free space, where the permittivity and the permeability are the respective values of those L and C parameters. Do you accept that?
That's the first time I've ever heard of it. I've always understood the speed of light to be not exceedable.
Okay, so that's a fundamental question I'm raising, but we can discuss it in more detail at another time. I certainly don't accept that conventional view, but I take it that it's posited.
Okay, so Slobodan has requested permission to share.
Yes,
so
that's good.
Slobodan, you do have permission to share your screen now. So let's see what Slobodan has to show us.
Actually, I have something on my screen, so I now suppose that I would be able to.
Yeah, there's a share button share thing on the bottom of your screen. You click on that, and then that will raise a menu, and then you can click right to share your screen, and then we'll be able to see what you're looking at.
Okay.
Do you see that?
The button on the right side of my screen.
Well, no, there's a button. First of all, there should be a button appearing on the center bottom of your screen, very dead center, that says share.
Oh yeah, okay.
See that? Click on that.
So, so do you see this here now?
No.
Not yet. No. But you do see the share menu, and then when you click that, there should be share screen.
Okay, I have sent you an email. Could you please just open the email and maybe do it yourself? Okay, thank you.
Okay, well, we can do it that way as well.
Yeah.
I haven't gotten it yet.
Middle of the email or something.
All right, still waiting for it. So did anyone else have any comments? So we've heard a couple different ways for this to be explained. So Harry explains it in terms of transmission theory, and it sounds like Slobodan's explanation seems similar.
Explaining this is completely erroneous and false, Franklin. Because
I would make the same assertion for your explanation.
You don't understand transmission line theory, and you don't understand the basics of electromagnetism, and that is illustrated by the fact that you have a basic fallacy in there where you're saying that a transmission line connected to its characteristic impedance is a voltage divider. That's not true. Okay, everything that we know in electrical engineering says that's wrong. Okay.
Well, even if that is wrong, then the only part of my explanation that wouldn't make sense is the 4-volt part.
Well, I mean, your whole thesis falls apart right there.
No, it doesn't. That just means that wouldn't be able to predict the 4 volts. Because the only thing that required is that that it be flowing out. That's really as like marbles. That's the only thing that it relies
argue
upon.
with
But
somebody
there is no
rational
marble.
like you.
Franklin, please, could you please show that email on the screen that I just sent you?
I'm
I mean-
still checking to see your email. Okay, I've got it now.
I'll show everything. I kind of, standing waves, your marbles, kind of fluid analogy, water, whatever. Yeah.
Oh yeah, this thing here. Okay. I'm gonna share my screen so you guys can see this. Okay, so there. This Slobodans. This is the one you want to see. These little plus minus thingies here.
Could you maybe expand it? Here, actually, the lower part. The upper part is just.
You want to see the upper part?
No, just the lower part, because we discussed the upper part, right? I mean, the upper part.
So you've got.
Okay, I mean, okay, the upper part, please just slightly, yeah. Actually, I took kind of a segment of the upper part, the inside of the coaxial cable. Could you show the upper part, right? And then show below how actually the field inside is structured. Actually, I can combine here kind of some pre-existing illustrations, figures, and so on. So if we go down there, I mean, to the lower part. So we have here kind of two, conductors, right? Maybe this is internally to the left side is kind of the central, the central wire, and the outside is kind of the cover of the coaxial cable. Electrical field actually is having this structure here. If you maybe blow up actually to put it on the screen, full screen, right, Franklin?
That's as big as I can make it, I think, because I'm displaying my screen on mail.
Yeah, I mean, kind of the flows of those marbles, your marbles, but those marbles are much smaller than the electrons themselves, So we have actually the flow. This is structured in this way. So we have flow in both directions and also circularly, right? So composed flow, and then it happens really that as though we have kind of bottle full of kind of pressurized fluid or water or whatever, springs, right? And then we open one side. Will you get back just briefly? I'm going to finish it. Franklin.
Just a second. I'm just. I forgot I was sharing my screen here. Sorry.
No.
There we go. Back to your.
When we open the one side, the right-hand side, by just putting the matched resistor there, actually those directions to the right, that flow to the right, starts going out because there is no, hurdle for it. Starts going out. The other flow to the left continues to the left, gets to the end, bounce back because there's much higher pressure at the border here than inside, because the inside fluid, inside gas, actually had been structured by influence of this battery. And then actually this starts going to the right, this to the left, and by that one going to the left, bounce back and starts comes to the right end of this coaxial cable at the moment when that flow that immediately started to go to the right gets out, and just keeps on it, continues, and 2 times long with the 2 times smaller amplitudes as detected. And you have also that overlapping that can be explained here. So I think we can find common ground here. I mean, with many discussions here, starting from the standing waves, electrons, and so on. I mean, having in mind and confirming actually that there is no flow of electrons inside the conductor. There is flow of structured ether or structured flow of some small subparticles of certain form that is a kind of magnetic field. We would have here to the right that kind of chunk of the structure of the field inside, put here on the right hand side, would have actually skewed those vertical lines. So we have longitudinal magnetic field and transverse magnetic field, or call it one or the other way, electric, magnetic. There is just small difference in the structuring of electric and magnetic field. I mean, when we look at this in this way, actually, electrodynamically based on the electrodynamics of Watzlawick.
So can you explain the 4-volt difference?
Which one?
Can you explain the 4 volts? Why is it 4 volts?
4?
Why is it 4 volts coming out?
4 volts? No, they are coming out two signals. That composed structure that consists of flows in both directions, longitudinally.
Yeah, but do you make a prediction that the measured voltage will be 4 volts? That's a very significant empirical result.
I mean, actually, kind of would be half of it, half of that one that is measured in statical situation. I mean, of course, that depends on the kind of how it is measured. But actually, you know, if it's something related to the pressure, you know, that you actually have a kind of that pressure being kind of divided in two, and actually having two flows starting in counter directions. And as soon as the flow that goes to the right gets out of the tube, gets out of the cork stable or the bottle, the other one, having been reflected from the left-hand side because of high pressure that is there compared to the inside of the chamber or whatever, it follows the suit going to the right and then start going out at the moment when the first one has completely exhausted, completely has gotten out. So 2 times longer.
Well, I mean, at the end, can you just like explain the waveform? Like I gave my explanation of why I thought the waveform at the last bit was the way it was. So I'm just wondering, do you have an explanation for why is the voltage
DC is actually how it is actually how this particular flow of ether, structured ether that we call static charge or static voltage is actually perceived by a particular detector, you know. That's static electric field, but inside actually it is not static, it's dynamic. There is no anything which is static in the nature.
Okay. Well, it seems that we are getting close to our. We're getting close to the end of our presentation here.
Particles for higher level structures, you know.
All right. Well, that's all stuff to think about here.
I can resend this to people who did. So, okay. Thank you very much for the opportunity just to illustrate what I was talking about. Thank you.
Okay, so that's what we're here about. We're here to give alternate explanations. No one needs to have any qualifications to give any explanations here. This is a science chat. So that as a moderator, it's important for me to allow everybody to speak freely, to speak whatever is on their mind. You do not need to be a university professor or expert to speak here in the science chat.
But we should be looking for some common ground for some to converge to some kind of common understanding, right?
Oh, that would be nice. But in all my years with working with the CNPS, I've never seen it happen. So it's just the way the beast works. So in any case, I need to summarize here. So So David, thank you for your question. He asked about the Wakefield experiment. And so I have, once again, I've listed the PDF here, so you can retrieve the document yourself. And so I'm not exactly sure exactly what Ivor Katz's explanation of this, other than it doesn't correspond to the normal capacitor discharge theory. But so Harry says that this can all be explained by regular transmission theory, whereby there's a wave that is just bouncing back from one end to the other. It takes twice as long. So that basically explains what's going on here. So, but that does interestingly kind of contradict Ivor's point that conventional theory may not be able to explain this, although there may be. So, and then we heard from Bill Lucas when we tried to corner him on whether electrons are actually flowing out of the wire, that, you know, that electromagnetics may be so incorrectly interpreted as to make the question to not even be relevant. So, and I'm not sure I ever really still got an answer as to whether electrons are things that flow in wires. I personally do, but we did hear some other ideas, like electrons are, you know, very, very large vortex structures, and it's kind of hard to speak to them as being little things. And then I tried to throw into the ring my own explanation as a physicalist and a positivist who loves the idea that electrons are these, in fact, these hard little balls that flow in wires. That I explained that this waveform can be easily explained if you think of the wires as the electrons as marbles flowing out of the tube. So, and I was thinking that you do have to explain the 4 volts. I explained that as a voltage divider, and I think that there are some other experiments when they change the resistance. I'll have to go check that again. But in any case, that wouldn't really affect my explanation for why the waveforms appear as they do when they step. That would just be a nit on what voltage is appearing as the intermediary voltage. But these are all very interesting things. So Slobodan, it would be nice if we could all come to a conclusion or try to get some agreement, but that usually doesn't happen. So it's probably more up to the people who haven't spoken during the chat, who just listen, who just want to get some different ideas, because believe me, once somebody gets their pet theory, they're gonna never ever let it go. So all you can do is pick amongst all the people who are trying to float their pet theories, and maybe you guys can come together and decide, you know, what makes most sense and have a consensus among you guys, because only people who don't have a dog in this fight can probably adequately decide what makes more sense, right? So that will do it for this science chat. And I would also like to remind you that on April 14th, Ian Cohen will be giving a special presentation on electrodynamics and the relationship between the waves between electromagnetic waves and versus other kinds of waves that we normally have, like those in sound and water. So I am looking forward to that, and don't miss that. And I believe I have a regularly scheduled science chat for next week. And just like David, if you've got a topic that you want to discuss, please just email it to me, franklinwho.com, and we'll be happy to beat it into the ground. If not, then I have my own standard list of things we're exploring with atomic data. So that will do it for this week, and we'll see you hopefully next week.
Thank you.